So, Jose, I think the floor is yours.
Okay, let's get started. Yeah, not no more delay. So welcome everybody. I'm very happy to start and kick off the webinar series of ethics. So this is the first of quite a series, and I'm going to share my screen so um, we can continue. So I think everybody should be able to see my screen, correct?
Yes.
So the first webinar is about strategic data acquisition, and it serves as an introduction to design of experiments, which is what we do at FX. FX stands for Efficient Experimentation, and the title of this webinar is Unveil the Power of Small Data. So as I said, thank you all for being here today. My name is Jose Núñez Ares, and I am co-founder of FX, which is a spin-off from K11 and a SaaS software company for design of experiments. In this webinar, we will dig deeper in examples and best practices of setting up an experimental design and doing the data analytics. And of course, if you want more information, please feel free to reach out after the webinar. Pharma, chemical, biological world, and also manufacturing is very complex. So the problems with experimenting in an intuitive way, like changing one factor at a time, is that nature doesn't play by those rules. And actually, design of experiments is the way to go, as you will see. We are dealing with data, and we like to call experimental design data small data. How do we difference with other kind of data like big data, which is quite popular nowadays? Big data appeared more than 20 years ago, the concept, and it was defined by 3 V's: the volume, the variety, and the velocity, which were very high for big data. Once the first analytical projects for big data, they were out there, they started seeing some issues or some hazards with big data, and they added 3 other V's there: the value, the veracity, and the variability. So the value of big data, it needs to be assessed, as well as the veracity, and the variability is in principle high because it's very heterogeneous. Small data, on the contrary, it has, of course, a low volume, low variety, low velocity, but it has a high value, high veracity, and low variability, which is very important, as you will see. Now, within this setting, what happens quite often at companies or research, some research departments, is that they have a lot of data available from previous experiments, historical data or production data. So the big data is already there. It may be in the shape of a database or multiple Excel files, maybe scattered a little bit. So the reactive approach is, okay, we have a lot of data. What can we derive from this data to solve one of the existing problems we have, for example? So in this case, the data is before, then we ask ourselves what is the problem that we can solve, how we can use that data, and then we proceed to analytics. This is different than the proactive approach with design of experiments and small data. The first thing you do is ask yourself, what is my problem? What is the problem that I want to solve, the challenge, and which data do I need to solve it? So this is the first question, which is very important because it decides and how you are going to acquire the data and generate the data. It's strategic. Afterwards, you do analytics. The comparison of this approach, these two approaches are that the data quality in the reactive approach is low because it comes very often from very heterogeneous sources. The volume is high. The acquisition cost is normally low. Much of the data may come from sensors or other devices. Very often, a big effort is needed to format the data and to get it into the shape you need to do the analytics. And the return on investment is uncertain. Is the sentence garbage in, garbage out. It's quite known in this kind of settings. Differently, the proactive approach and the quality of the data is very high and the volume is very low. Don't forget, we are talking about small data. Acquisition cost is normally high. And why? Because getting every data point is normally expensive. That's why we think so carefully on how we're going to gather the data. There is no format needed for analysis, and the return on investment is high. In a nutshell, what is small data? Well, the small data is collected in a controlled environment, and it is documented so it can be reproduced and transferred. It is structured. It is there to solve specific use case. It's very usually expensive to obtain. And it can be extended without loss of quality. So if you need further information, you can reuse the data that you already have and minimize the next experimental effort. Because it has so much quality, it allows for knowledge discovery and uncertainty quantification, which you will see is very important to draw the conclusions out of this small data. Gathering small data as is normally tackling complex challenges is a collective effort of a group of stakeholders. So it also helps the implementation of a culture of measurement and data. What is a use case, typical use case for design of experiments? Well, it is very simple. On the one hand, you have some inputs that they affect a product or a process. And on the other hand, you have the quality of the product or process or outputs that it consists of several quality attributes of the product or the process. It can be applied to food industries like Pringles. This is a real case we have done in the past. Pharma companies, semiconductors, manufacturing, and so on. The goal is to choose the right inputs to get the best quality. How do you do that? Well, everything starts with a brainstorming where all stakeholders or people that they know most about the process, the experts, they gather and they discuss and identify all sources of variability. So what is this? Is all input parameters that they affect your product or your process. Importantly, they also set the goal of the experiment, what they want to achieve. On the one hand, it could be that they want to identify the most important inputs. On the other hand, it could be that they want to optimize the process and get the most efficient values of the inputs, so operating conditions of the system, so the product is as best as possible. It is a very documented process where also the measurement is assessed, so the precision of the measurement is taken into account. Maybe some extra experimentation is done to assess how precise our measurement system is. And importantly, there is a protocol for the experiment. So think that when you perform an experiment and you gather the data from the test, you need to be as rigorous as a scientist. It is very important not to include systematic errors during experimentation. All this previous work ends with the selection of the test that you are going to perform that maximize information and minimize the number of tests that you do. So this trade-off is something that we always take into account to maximize the information, but minimize the cost of the experiment. It doesn't end there. It's not just about gathering data. So the preparation, setting up this experiment, conducting the experiment, analyzing and optimizing, which is the conclusion, are the 5 steps of a successful DOE, or as we call it, design of experiments, flow. So every step is important, and once you have the data from the experiment, so once you are done with phase 3, you can analyze the results, and there is where you replace the data you have with a mathematical model that allows you concluding about your experiment. If you use DAOE, what do you get from it? Well, many things. So first, you will save costs. You will test more efficiently and save costs because you minimize the number of tests to obtain your goal. And that is because of the planning involved in a design of experiment. Because it's heavily based on scientific methods and statistics, it allows knowledge discovery. And differently than other machine learning or AI methods, the models obtained with the design of experiments are explainable. So they allow to discover and quantify the influence of the input parameters in the output. So not only the main effects, for example, how much specific input affects the product, but also the interactions, because there may be two-factor interactions between 2 different inputs, and you can also detect those. Because of the scientific methods behind design of experiments, the knowledge is transferable. We have had in the past, well, and still now, sometimes when we go to a company, we find that the process they are concerned was everything about the process. So the quality of the process gets retired, so the knowledge goes away when this person is not there anymore. With design of experiments, you can extract the knowledge from these key people and transfer it to either other plants that they make as similar product, or to other people. So you implant culture of data-driven decisions. Because the data is taken under very controlled circumstances, we assure the reproducibility of the results. As I said, it's not only about gathering data, and it's not only about concluding. So design of experiments is essential in a continuous improvement setting. So imagine, I mentioned here 3 different cases of conclusions that you may have after finishing an experiment. The first one, after you analyze and optimize the data, you find a set of operating conditions where your product has the best possible quality. Now there is a follow-up that will be to run some confirmatory runs, so you can assess that your conclusions were correct. Second conclusion you could have after you perform an experiment. Imagine it's like 20, for example, and you want to identify and spot the most important ones. In this case, when you spot them, you want to study them further. So this first experiment is continued by another experiment, which is called an optimization experiment. The third case. So it could be that your goal is to find the best set of operating conditions, but the analysis suggests that you should expand the ranges of the inputs. So you should If during the experiment, for example, you tested the temperature from 400 to 600, maybe the analysis suggests that you should explore a bit higher temperatures because there may be better alternatives for operating conditions there. In that case, you can augment the experiment and add more tests to the data and reuse the data that you have collected so far. Now, next section is about 3 different types of experiment that you can plan. So you see more concrete examples of what this methodology can offer and can help to achieve. Screening experiments. I already told you a little bit about this kind of experiment. In this setting, you have a large number of inputs that they may influence your product or process, and you have to screen out the most important ones. So these kind of experiments are normally very small experiments with a limited number of tests, but very efficient in identifying the most important inputs. Here you see some examples that we collected from literature. It's a kind of random example just to show you the high applicability and versatility of these kind of experiments, that they can be used in pharma, they can be used in 3D printing, they can be used in food industry, and so on. So this is the first kind of experiment that you can perform. The second is an optimization experiment, and this is a little bit a different setting. Here is where you want really to get your product or your process to the best possible state. And for that, you have already identified the most important inputs, and you want to get best values for the inputs such that your process is as best as it can. Normally, these designs, these experimental designs are a bit larger, but they allow a very, very detailed mathematical model, so you can get good conclusions out of the data. Again, remember, it's always small data. As before, here you see kind of random selection of articles using optimization designs in electric vehicles, in, again, gelatin making, in pharma, and so on, in biodiesel production. So it is very, very generic technique. Third example is more on material variability. So very often, and it is very common in the food industries, but also in the chemical, you work with raw materials, and the raw materials, they have variability. Think in this case that is presented here in the slide, where there is a company that makes malt, and they, of course, use raw material, which is biological, and they have some production process parameters, so some temperatures, pressures, times that they can change in their process. So all this together, it goes into a plant, and they produce the end product that needs to be within certain specifications. The raw material is what we call in our jargon, in the lexicon of design of experiments, is an uncontrollable input, because you cannot really control, for example, the content of fat or the moisture of the raw material, but you can measure it. So you can include it into the analysis, and in the end, obtain a mathematical model that will tell you which production process parameters are best to use depending on the raw material that you get inside the company. To sum up what we have done, well, we have seen how strategic data acquisition obtained from design of experiments can efficiently enhance product and process performance by being a proactive approach. minimizing the sources of variability, and allowing knowledge discovery and transfer. As we have seen, it's not only about gathering data, but also analyzing and optimizing the mathematical models from the analysis. So there are 5 steps uh, that they are in a circle because, as you have seen, the DOE process can be cyclical, and the 5 steps are the preparation, then designing the experiment, which is deciding which tests to perform, then conducting the experiment. Once the data is available, you analyze the data and model the data, and finally you optimize, drawing the conclusions. You have also learned that there are screening experiments, optimization experiments, and robust experiments. So this ends the more theoretical part of the presentation, because the last 5 minutes, I am going to show you FX software for design of experiments. So the software demo has a use case, and the use case comes from an article, and it's about the optimization of tires ingredients. So in this case, we have 3 different inputs or factors that they are ingredients of a tire, right? Like a car tire. There are 2 responses, which are outputs that they describe how good the tires are. This is the elongation and the abrasion. And the ingredients of the tires are the silicon, the silane, and the sulfur. The goal of the experiment is the optimization of both responses at the same time. So it's a multi-response optimization problem. Here, I recap the 5 phases of design of experiments. The preparation we have already done. We have identified the sources of variability, the 3 inputs. We have also defined the goal of the experiment and the 2 responses of how we are going to measure the quality of our product, which in this case are tires. Setting up the experiment, analyzing the results, and drawing conclusions is what we are gonna do using the software. I'm going to change to the software now. So here we are. This is the software. It's a web-based software that we offer and covers, as I said, the 5 different phases. So the first thing, now that we have identified which inputs they influence the quality of the tires, is to obtain an optimal design for it, so an optimal design experiment. And for that, we go to guided DOE, and we add the quantitative factors, because all these factors are quantitative, and we follow the flow of the software. We will also indicate how good we want to model the data, and that is related to the number of tests that we will perform. In this case, let's say that we have a budget of 15 to 16 different tests. So each test, gathering its data point, is expensive, because in this case, you will have to process and manufacturing a batch of tires. Then we can click next. This is some criteria that we use. It's a bit more technical, so this will be explained in a future seminar. But importantly, you can just launch the calculation. Then the calculation is submitted, and in the servers of FX, this calculation is done. Calculation is ready. You get notification, so we can click and see the designs that we have. I'm going to go fast, because in this case, we will have a separate webinar to explain how to select an experimental design. But let's say that we have a recommender system that will help you in choosing an experimental design for your problem. And again, an experimental design is a smart combination of the values for the inputs that you're going to test so that you get the most information out of it. So you can get the experimental design as easy as downloading the design, giving it a name, and then specifying every single factor, the name and the lower level. Level, let's say, goes from 20 to 40, and you can do that with all three different factors. And finally, get the design, which is actually an Excel file that is open in another screen I have. So which is an Excel file will, no, sorry, it's not this one. It's an Excel file that will tell you, okay, you will perform 15 different tests, and the first test you will use a value of silica of 20 and so on. So this is the design that you send to the scientist or the operators that they will perform the experiment. And in the end, you will have this data set. This data set is the experimental design, which is on the left part of the table, and then the two different quality attributes of your product. Okay, let's see, you cannot see the design. Yes, please give me a second. Now you're able to see the design and the data. So this is the experimental design that came from the software. So it tells you which values for each factor you are using, and this is what is sent to them, to the operators, and then they measure the aberration of and the elong. And this is the data that you get into our software for analysis. And to get it into our software is as easy as copying the data, going to modeling, then copy pasting and indicating that here you see the table. The software is smart to detect if the factors are quantitative or not, and selecting that these two last columns are actually output responses. You give it a name, and then you are ready to go to the next step, where we will select the different outputs and select them for analysis. And this is as easy, and there will be a next webinar, but you have a few parameters that you have to enter to launch the modeling. Launching the modeling sends the data again to our service, so we have a web-based app, and you get a notification when the calculation is ready. So the calculation is ready, and then you can select the models. So you select the models for each response. And right now we are going just to select the recommended model. We have a recommender system where we can select a model for each response. So abrasion and elong. And we select the model. Now we have selected the model, so you have to consider that we have found the experimental setup the experiment was conducted. We have analyzed the results, and now we are going to draw the conclusions on the data. So to that, we can go to optimization, and there is an easy way to set the specifications. So remember, we have tires. The abrasion needs to be minimized and less than, let's say, 140. And the elong needs to be on target. So we can set the specifications that we need for each one of the quality attributes. And we can optimize it. So we have this parallel coordinate plot where the specifications of the responses, specification limits, they are taken into account. And here you have parallel coordinate plot where you can optimize your problem and choose the best values for the inputs such that your outputs are within specifications. So here you have the inputs, so 3 inputs, a discretization of the input space with 2 values per input, and then here you have 2 responses. You have the prediction of each one of the responses and the probability of success of being within specifications. And this is a very powerful graph because you can have a very high discretization level, as you see. You can have 11 points per input range, and then get the best points that will render your product as good as it can. So it's very interactive graph. There will be more information coming up in a webinar, but the accompanying table gives you the best points, so the best values for the input, such that the output, your product or process, is as best as possible. And this ends my presentation. And I want to thank you for being here today and for your interest in the topic of strategic data acquisition. And as said before, this webinar is the first of a series on how to experiment more efficiently using this kind of experiments. And the next webinar will be on January 13th. And if you want more information or you want to book a demo, so we explain the software to you in more detail, please go to fx.app and reach out to us. So thank you, and I will be happy to answer any questions if there are questions in the chat. So I think there are no questions. So yeah, thank you again for being here, and see you next time.
Bye also from my end, and see you next time. Bye.
Bye.